ஆரம்பிச்சிட்டுங்கிறா.
Nagarajan sir, can you hear me, sir?
ஆரம்பிச்சிட்டுங்கிறா.
Nagarajan sir,
Ma'am, all set, ma'am. You can start the session.
okay.
Is it audible, ma'am?
Yes, ma'am. Yes, audible, sir.
Okay.
Sir, you can
So,
start sharing your screen, sir. I have given you co-host privilege. Then
Yes,
share
sir.
your screen.
Yes, sir. Thank you, sir. Is it visible, sir? My
Yes, sir. Yes.
PPT?
Yes, sir.
full screen வச்சுக்கலாமே.
Sorry, ma'am.
Full screen. Make up full
I
screen.
enabled. I
Okay.
enabled.
Okay, okay. Sir, may I start, sir? Ready, sir?
Ma'am, proceed. Proceed, ma'am.
Okay, sir. Okay, sir. So, good evening to one and all present here.
Good evening, ma'am.
Good evening. Today is the 5th day of AACT sponsored, Academy sponsored 6 days online faculty development program on AA assisted integration of renewable energy sources into EV charging networks. So today also we have a 2 session. In a 2 session we have 2 resource person. In first session, A. Kannaparan sir, Associate Professor in Shastra University, Tanjavur. In a second session, we have another one resource person, Dr. Arunya Revati ma'am from AC Tech, Karekudi. So first session, I hand over to our resource person, Kannaparan sir. So before starting the session, some introduction about our resource person.
Shall I start, ma'am?
1 second, sir. He has completed BA in Anna University, Chennai and completed MA degree, master degree in power trans and drives in AC Tech, Karekudi. Now he is working as a associate professor at Shastra Deemed University, Tanjavur, Tamil Nadu. He had published more than 20 international journals and presented more than 10 papers in international conference. He is a world expert in power trans converters for the integration of renewable energy sources and electric vehicle battery charging system. Welcome you, sir. Welcome you for our session.
Thank you, ma'am.
Welcome you, sir. Okay, sir.
Thank you, ma'am.
Now you start, sir.
Okay. So, good evening, faculty members, coordinators, and participants. I'm Kannaparan from Shastra University, Tanjavur, Tamil Nadu. It is my privilege to address you in this faculty development program on the topic AA algorithm development on AA assisted integration of renewable energy sources into EV charging networks. The transition towards electric vehicles and renewable energy is not only a technological shift, but also a societal transformation. As a researchers and educators, it is vital for us to understand how artificial intelligence can help bridge the gap between the renewable energy, variability, and the demanding requirements of electric mobility. So, from the title suggests the focus is on developing AI algorithms to facilitate the integration of the renewable energy sources such as solar and wind into electric vehicle charging networks, simply known as EVCNS. So the outline of the presentation follows. First, going to explain the need for AI assisted integration. to highlight why AI is necessary for this integration. Then the system architecture, the high-level design of sensing.
Professor, slides are not changing.
Oh,
Still first
sir,
slide is showing.
can you able to see the presentation outline, sir? Is
Yeah,
it
first
visible?
slide is showing, but not able to see other slides. Maybe you can go for slideshow so that you can
Sir,
comfortably
actually,
move from-
I enabled the like that only, sir. Otherwise, shall I change the slide like this? Is it?
Yeah, that's fine. That's fine. Manually also you can.
Yes, sir. Yes, sir. Thank you, sir. So this is the outline of the presentation. Follows. First one is we are just going to see the need for AI-assisted integration. So to highlight why we go for AI and it is necessary for this integration. Next, the system architecture, the high-level design of sensing, prediction, optimization, and control. Then the AI algorithm development pipeline, how the raw data is converted into real-time charging decisions. Then forecasting models, short-term models for renewable generation and EV demand. Next, optimization and control, especially the methods such as model predictive controls and reinforcement learning. Next, multi-agent coordinations and P2G, vehicle to grid. So distributed approaches for large-scale EV networks. Then evaluation and benchmarks. So how we measure the effectiveness. Next, deployment, cybersecurity, and ethics to meet out the real-world considerations. And finally, the conclusions with references.
Excuse me, kindly put in the slide mode.
Yes, sir. Actually, initially I enabled slide mode also. Can you able to see the change in slide, sir? I changed the slide now.
Yeah, change.
Okay. So is it visible, sir? Need for AI assisted integration. Can you able to see the third slide?
No, sir.
Okay, I will change manually, sir. No problem. I will change it manually.
Need for AI assisted integration is seen. Thank you.
Yes, sir. So now we're going to see the need for AI. So let us begin with the need for AI, right? So first, the integration challenges. The renewable sources like solar and wind are intermittent. Their output fluctuates with the weather conditions. Second thing, the EV arrivals at charging stations are stochastic. The drivers arrive unpredictably with a different state of charge and urgency. The third one is the tariff variability with the dynamic pricing and demand charges. So it adds the further complexity of the system. And finally, the grid constraints and battery degradation. So that must be managed carefully to ensure safety and the longevity. So these are all the challenges in the EV RES integration. So we go for the AA objectives, right? So in the AA, the main objectives are listed here. The first one is to minimize the cost and emissions simultaneously. The next one, maximize the renewable utilization and system reliability. Then to give a respect physical limits of the grid. So the grid reliability, safety, security must be assured, including the voltage, current, and the feeder capacity. And finally, the guarantee quality of service by ensuring that the EVs are charged within their deadlines and the SOC requirements. So in short, the AA provides the intelligence to balance these competing objectives under the uncertainty. So without AI, operators must rely on simple rule-based systems which are insufficient for the scale and the complexity of the modern EV networks. So the next one is the system architecture. So the system consists of the following components, and the data flow and KPIs are shown in the slide. So the key components of the architecture actually consist of the renewable energy sources such as the photovoltaic and the wind, and the electrical which can supply or the electrical grid which can able to supply or absorb energy, and then the battery energy storage systems to buffer the supply-demand mismatches, and finally, the V2G capable of the EVSE, that is vehicle-to-grid operations. And the communication protocol actually that involves the edge gateway to reduce the latency. So in a local area interface, right? So the edgeway gateway that edge performs local inference on fast control, and it ensures the low latency. Then we go for the cloud server, right, interface. The cloud server handles training, analytics, where more computational power available. And the following communication protocols used in the components to create the communication among the various components. The OCPP for charger interoperability, ISO 15118 for vehicle to grid communication, and then MQTT or IEC 61850 for data streaming. So we'll see these communication protocols actually in detail. So this OCPP stands for the Open Charge Point Protocol. So it is a standardized communication protocol used for communication between EVs and charging stations, and a central management system, simply known as CSMS. So the main purpose is to ensure the interoperability between EV chargers and software from different manufacturers, so that we go for OCPP. It allows the EV charging networks to monitor, control, and manage the multiple charging stations more effectively. And also it supports functions like remote operation, start, stop, and then result diagnostics, and it allows to update the firmware, and as well as we can use it for doing transaction also. So the transaction management also that can be done with the help of the OCPP. And actually different versions are available. So the latest version, OCPP 2.0 and 2.01 available. It came with the enhanced security, smart charging, and the better diagnostics. And this OCPP offer the following key features. The first one is about the session management, authorization, remote control, smart charging, diagnostics and firmware update, and finally the transaction loggings and reporting. So these key factors offer the main benefits like promoters vendor independence, it facilitates network scalability, it enhances grid integration and energy management, and finally it supports the future smart charging and the vehicle to grid features.
Well,
So this is what
change.
about. Sir, actually, I'm just keeping this only, sir. Just I will explain each communication protocol in detail, sir. Yes, sir. I will change manually, sir, one by one, sir, the slides. So this is the OCPP protocol to create the connection between the EV and the CMS, that is charge station management. The next protocol is about the ISO standard 15118. So it is an international standard that defines the communication interface between the electric vehicles and the charging stations. So it is mainly focusing on smart charging and vehicle grid integrations. So the main purpose of this protocol, it enables plug and charge functionality, and the EV can automatically identify itself and initiate payment at the charging station without needing the RFID cards and any applications. Then it facilitates the bidirectional communication between the EV and charging stations for smart energy management. And it supports vehicle to grid operations, allowing EVs to feed energy back to the grids. So why? Because whenever the grid are disturbed by more that is chargers, we can go for V2G operations. So we can return the energy back to the grids to maintain the grid reliability. And it offers the following key features like plug and charge, smart charging, bidirectional energy flow, security, and standardized communications. Actually, it works over all the power line communications or other network protocols between electric vehicle and the charging station. And it offers the following benefits like convenient operation of automatic authentication and payment, then energy efficiency, and interoperation. That is interoperability. It works it works across all multi-brand EV charging infrastructures, and it is future ready. It enables V2G and smart charging for renewable energy integrations. So we can simply compare this ISO 15118 and OCCP protocol. So each one has its own benefits, merits, and demerits. And finally, you're going to see the MQTT protocol IEC 61850 for IoT interface. So whatever the communication we discussed so far, that will be done only within the charging infrastructure under the EV, and the MQTT IEC 61850 that exchange the data to the user. First, we will see about the MQTT. So MQTT means message queuing telemetry transport. The purpose of the MQTT is a lightweight messaging protocol. This is designed for real-time data streaming, especially in IoT systems. So why? Because nowadays we communicate through the smartphones to the internet. So with the help of the internet platform, we can exchange the data, we can communicate the data. And it is commonly used in EV charging, smart grids, and remote monitoring, where bandwidth is limited or devices are resource constrained. Actually, EV chargers that are publishing actually real-time data like voltage, current, energy consumed, SOC, everything to the cloud server, and smart meters sending the live power readings to energy management systems. So this is what about MQTT. Alternatively, we can use IEC 61850 protocol also. Actually, this is an international standard for communication in electrical substations now, and it is extended to smart grids also. So it defines the data models, messaging, communication services for production, control, and monitoring of electrical devices. And it has the following key features. It is like object-oriented data modeling. So devices exposes their functions as standardized objects. As a result, actually, it supports the interoperability. So again, similar to the previous protocols, what we discussed in the OCPP and ISO 15118, it also allows the interoperability, allows equipment from different manufacturers to communicate seamlessly. And its scalability nature, it supports a large scale system like substation, microgrids, EV charging networks, etc. So we can compare this MQTT and IEC protocol 61850, and based on the merits and demerits, we can select the suitable protocol in a real-time implementation. So this is what about the components which are present in the architecture. So next, what we are going to see the data flow and the key parameters. So data flow and the KPIs. So the data flow in EV charging systems, actually it describes how the data moves between the different components. Why? Because we need to, so various protocols and various system components we discussed in the previously. So the next thing, how we can exchange the data from one place to another for the sake of better communication and to process more effectively. So first, the data moves between different components in EV charging ecosystems. So typically it involves the components, EV vehicle, then charging station, then various communication protocols used to what we discussed in the previously, and then the data flow sequence like this. So EV connects to charger. So charger initially will create a handshake signals for the sake of authentication and to plug and charge. So here ISO 15118 handshake protocol used here. So whenever we connect the vehicle to the charger, this protocol will be enabled. Then charger communicate with the backend. So again, the OCPP protocol will be enabled. It starts to send the data. So it starts transaction and it measure the meter values and the session status. Then to communicate with the aggregator and the user, the MQTT will be called for the real-time telemetry to the cloud analytics. So this is how the data flow takes place. and then the backend or cloud processing. So after data aggregation, billing, and the key performance indicator calculations and alerts, this will be sent to the cloud processing. And the fourth one, the data reaches the user as well as the grid operator or the aggregator. So they can visualize the data through the dashboard or any applications like Android or iOS applications. So they can check what is the current status, what is the battery health condition, what is the battery SOC, and what is the process going on, whether charging or like vehicle to grid or whatever it is that can be visualized right to the user and grid operator. And finally, the grid feedback will be taken into account to implement the vehicle to grid commands. So if we want to perform the vehicle to grid commands, the input from the grid aggregator must be received, and then based on the AI decision and the customer feedback, the V2G command will be implemented. So this is what the data flow works. And then the next one is about the key performance indicators. So I'll change the slide. Sorry, actually KPI is not yet over. Sorry. So first we'll complete the KPI also. The key performance indicators. Actually, various key performance indicators are actually there. So KPI is nothing but what measurement parameter. It is a metric to measure the performance, reliability, and efficiency of the EV charging operations, especially. So there are 4 different KPIs are there. The first one is the operational KPIs. So the operational KPIs that shows the charger availability, utilization rate, then mean time to repair, like average time to fix the faults. Then session success rate. So the transaction completed successfully. Okay, the completed, that is successfully completed a transaction will be displayed. And second KPIs that belongs to energy and efficiency. So in this energy and efficiency KPIs, actually there are 4 listed here. One is the energy delivered, so total amount of power supplied to the EVs, and then the average charging power, that is efficiency of charging sessions. So how effectively charging time. Then the charging duration, so how long the charging takes place. So average time per session will be measured here. And then finally the peak load. So the highest power drawn during the operation, all those things will be measured under this metrics, energy efficiency KPIs. And then the next key performance indicator, the third one is about the financial KPIs. So the financial KPIs that list the revenue per charger, that is earnings per station. Okay, whether we can do charge or we can do to the vehicle to grid operation. So the revenue per charge will be measured here in the financial KPIs. And then revenue per kWh, that is earning per energy delivered, and then the cost per session. Finally, these 3 are the KPIs that belongs to financial KPIs. And the last one, the fourth one, that deals with the grid parameters, especially, right? The grid or smart charging KPIs. So here, the load factor, the renewable energy utilization, the V2G participation, everything will be measured in this using this grid or smart charging KPIs. So this is how the architecture works. So the left side you can see the typical components present, and right side you can see how the data communication done, right, using the protocols what we discussed previously. So next what we are going to see how the AI algorithm deploy, that is development pipeline. So how the flow will be there, just we are going to see in detail here. So this AI right algorithm development pipeline is a step-by-step process actually. Okay, so various steps are involved here for the designing, building, testing, and deploying the AI models to make the data-driven decisions. So in EV or energy applications, right, it could be involved predicting energy demand. So two things we must done through the AI. The first thing is about predicting the energy demand. Okay. So in advance we must, why? Because you know your conventional mathematics will give an answer only after the proper calculation. But what we need we need to forecast, we need to predict the energy demand right in advance so that we can plan accordingly. And second major thing is about to optimize the charging schedules. So optimizations will be done based on the predicting energy demand or detecting the equivalents, right? So this is what about the basic of the AI algorithm development. So two things are involved. One is the predicting energy demand. The another one is optimizing charging schedules. We'll see one by one. So first, the pipeline stages. The stage one involves the problem definitions. Okay. So what objectives? So we need to define the goal of the AI system. For example, to predict the EV charging demand at a station, or to optimize grid load using vehicle to grid, or to detect the equivalent or anomalies in energy consumptions. Okay. So these are all the typical examples. And as a deliverable, we can get the clear KPI targets. So KPI, you know, the previous slide we discussed, right? So we can get the metrics. So what are all the things required, right? The KPI targets, that the success criteria and the constraints. So this is what the stage one. And stage two, the data collection. We need to gather the relevant data from the various sources. For example, from the EV, the SOC, the battery voltage, current. So all those things must be gathered. Second thing, from the charging stations, we need to get the informations like sessions, then energy delivered, and the fault conditions. All those things need to get from the charging stations. Then we need a grid data also. What is the current voltage, frequency, and load delivered from the particular grid? And in addition, we need to know the weather and renewable generation data, especially for smart charging, right? And along with the protocols, what we discussed previously, like MQTT, OCPP, IEC 61850, cloud database, everything will be used here to perform this data collection, right? So this is the second stage. And the next stage is about the data pre-processing. So in this data, yes, sorry, is it audible? Okay. So in the data pre-processing, actually, you know, we need to filter the data what we received right from the system, especially from the EV charging stations. Why? Because it is raw in nature. So we must remove the missing data, and we must remove the duplicate data or the corrupted entries, right? So these are all the things will be done in the data processing. And we need a normalization process also. Why? Because when we try to interface with the AI algorithm, the scale numerical values must be normalized for AI algorithms. And then we need to create a meaningful features, right? Like the data must be converted into the time of day or weekday or weekend or SOC or any trend analysis like that. We need to convert the data. And finally, it must be labeled for supervised learning. So the label historical data like peak load or normal load will be processed. So this is how the pre-processing done. Then the next stage is about the model selection and development. So in this model selection and development, we need to select the AI or ML algorithm based on the problem. Okay. So for example, the regression type that predict the energy demand, the classification that detect the faults, the clustering that group the charging patterns, and the reinforcement learning RL that results smart charging optimization, right? So these are all the different model selection for the development of the AI/ML algorithms. And various tools are available. The various tools and frameworks are available like Python, TensorFlow, PyTorch, Scikit-learn. These are all the tools available in the market. We can use it for the AI and the ML algorithm implementation. And the next one is about the next stage, the fifth stage is about the model training and validation. So after getting the data, after the pre-processing and after we design the model using AI and the ML, it must be properly trained, right? To perform the two requirement what we already discussed, right? To predict the energy demand and to optimize the charging schedules, right? So we need a proper training. So we need to feed the pre-processed data to the model, and it must be properly validated, right? So validation that involves evaluate model of performance on unseen data. So unknown data must be properly processed to validate the developed model using the AI and the ML. And then the various KPIs, the metrics, what we discussed initially, will be used here to measure its accuracy and then the forecasting nature, right? And finally, the tuning. So tuning is essential to optimize the model parameters for the best performance. So why? Because after proper learning, that it starts to work towards the optimized results. And the final stage is about the implementation, the deployment. So after a successful development of the model, we go for a deployment, right? So here we need to integrate the AI model into two production. One is the edge deployment and another one is the cloud deployment. In two different ways, the developed model can be utilized. The first one is the edge deployment. So in the edge deployment, we can directly we can implement it on charger or gateway for real-time decision making. Okay, so it will not connect with any other external source. In the charger itself will take a decision. So what rate we need to charge the battery and all other decisions will be taken in the charger itself. The next one is the cloud deployment for large scale data processing and analytics, and everything will be monitored. So we, apart from implementation and the effective implementation of the system, everything should be monitored. So a track model performance in real time will be used here for the monitoring. So this is what about the flow of the AI algorithm development pipeline. So the next one is about the forecasting models. So we need to consider the renewable generation and then EV demand and arrivals. So these are all the forecasting models for short term used here, right? So this framework actually integrates the AI forecasting with the optimization and control. So it forming a closed loop smart charging ecosystem that balance the cost, emission, and user demand. So actually we prefer the heterogeneous means, like what different data will be collected and all the data will be processed, right, to get the information about the renewable generation. And these are all the models used in the forecasting for renewable generation. Actually, the ML and DL, actually XGBoost, SVR, LS, PM, CNN. We will discuss everything in the simulation, right? Along with mathematical models. Just right now, I'd like to display the different forecasting models available, right? For renewable generation and the EV demand arrivals. So next what we are going to see the optimization objectives and the constraints. So the optimization aims to balance the multiple goals in scheduling renewable generation, battery storage, and EV charging. The very first one is about the cost minimization for both energy and demand charges. So energy charges here, the total electricity consumed from the grid priced at the time of use are real-time tariffs. And demand charges, that includes the extra cost for peak demand. So that optimization reduces the simultaneous high charging loads. So this is what the objective function used in the cost minimization. The next one is about the emission reduction, especially the carbon intensity, okay, and the corresponding aware dispatch. So it schedules charging and discharging based on the grid carbon intensity signals, preferring the renewable generation over the fossil based power. And the next objective function is about the quality, right? The quality of service, QoS. So we must ensure the user satisfaction by minimizing the wait time at charging stations, right? So especially during peak load, the wait be reduced. So to minimize the wait time at charging stations, and at the same time, we must guarantee the SOC, right? The state of charge targets before the departure. So whatever the SOC, maximum SOC, the battery must be completely charged before departure. So these are all the things considered in the QoS to minimize wait time, guarantee SOC targets. And finally, about the battery. So the cost of the battery is very high, right? So we must consider the battery health also. So when we prefer the high charging rate, we can reduce the wait time. We can charge the battery very fast, but at the same time that results battery degradation. So the life cycle will be affected. So we must carefully consider that battery cycle also. So that models include the degradation cost for batteries. For example, the batteries used in battery energy storage systems and EV batteries. So the optimization avoids the frequent deep cycles and the high C rates. Okay, so frequent deep cycle results the battery health, you know that, right? And the high C rate also results the poor battery health. So in order to extend the battery lifetime, all these things will be considered under the objective function. So these are all the 4 different area. We can consider either one or the combination of more than one when we coin the objective functions. So tomorrow simulation class will discuss about all the objective function, possible objective functions, and then we'll try to run using the AI model to get the output. The next one is about the various constraints. What are all the constraints we need to consider, especially for the optimization? So we discussed about the various objectives, right? To achieve the objective, what are all the constraints required? So the following constraints are taken into account. The first one is about the feeder capacity. So the total power drawn should not exceed the feeder limits. So why? Because that in electric, actually the power delivery will be already scheduled, that is already planned. So we should not extract more power, whatever the limit which is there already. The second one is about the voltage and current limits. So we must maintain the safe operating conditions for the distribution network. At any cost, the grid stability should not be affected. And the next one is about the charger ratings, and then the connectors availability. So the power limited by charger hardware specifications. So charger ratings where the power must be limited by the charger hardware specifications. So it should not affect, it should not take more current, whatever the rating mentioned in the charger. The second one is the connector availability. So users cannot be scheduled to charge if all connectors are occupied. So we must consider the connector availability also as one of the important constraints. And third one is about the battery energy storage system constraints. Especially, we must know about the boundary of the SOC. So what type of battery used and what is the possible limit for charging and discharging. So we must avoid the charging and discharging above the limits, right? So the SOC must remain within the safe minimum and the maximum levels. So typically for a lithium ion, we prefer 20 to 90% of the SOC. So less than 20%, actually the battery management system BMS will stop to discharge. So it gives alert to charge, and similarly more than 90%, it will not allow you to charge further. So you know about CCCV. So CV will try to maintain its terminal voltage constantly. No charging will be done after 90%. And the number of cycle limits. So to avoid the excessive charging discharging cycles, to limit the wear. Okay. So frequent charging and discharging of battery must be limited. So it is discussed under one of the constraint cycle limits. And finally, the user deadliness and the contract rules. So EV must reach desired SOC before user departure time. And then the contractor rules also one of the constraint from the user end. So some users may have subscription plans, priority contracts, or guaranteed service levels. All those things must be taken into account to optimize the objectives. So now we are going to entering into the solvers. So what type of solvers the AI is going to use? So actually, AI, it is not a single tool to handle all kind of constraints and do all kind of operations. Actually, it will select the different programming method to perform the various operations during the data flow. So first one is about the mathematical programming. So deterministic optimization methods widely used when problem can expressed with the equations and the constraints. So we prefer normal mixed integer, linear, or quadratic programming, right? So this equation can be easily solved, and we can get the solution directly at a very short span of time. The next one is about the meta heuristics method. In this, we go for GA, PSO, simulated annealing, this kind of programming method. So when we have a huge amount of data and the number of data and the relation among the parameters becomes more complex, we go for the meta heuristic. And for the forecasting, we go for the reinforced learning, so RL. So Q learning, DQN, PPO, SOC. So these are all the various methods used in AI, right? So the learning based approach where agent interact with the environment and optimize long-term reward. So the actually meta-heuristic method will just to work with the existing data set, whereas the reinforced learning will get the current data and it starts to work towards the data available. So these are all the various solvers and the meta-heuristic methods. And so AI, which is going to utilize these to predict the demand as well as to optimize the objective. So the next one important thing is about the model predictive. So whenever the system contains more constraints and more nonlinear relationships, so we go for model predictive control, right? So a similar structure using mathematical model will be developed, and the response from the mathematical model will be taken into account to find out the response from the real-time system. So actually MBC structure that the receding horizon with updates forecast, and it handles constraints natively. And it integrates use forecast as exogenous inputs and from the previous schedules. As a major benefit of the MPC, that gives robust to disturbances, especially during the dynamic change in real-time scenario, and also gives interpretable control, right? So this is what about the main advantage of the MPC, and also the following points must be considered, especially the solver speed and the constraint tightening as well as the feedback policies. So this is what about the MBC, the model predictive control. Then deep RL, right? That is the reinforcement learning for smart charging. So in the deep RL, actually for smart charging, we have the following MDB formulations, right? So actually, in short, actually MBC provides a real-time adaptive scheduling by combining the optimization, forecasting, and receiving the horizon execution, right? So it is a little in advanced when compared with the meta-heuristic methods. So actually MDB formulation, it model the scheduling dispatch as an MDB, right? So the state of charge, queue, forecasting, prices, all those things will be considered as the state, and charger set points, then the power rating of BES, then V2G constraints, all those things are taken as action, and whatever the cost, emissions, and weight penalties will be considered as the reward. So like this, actually, the MDB is formulated, and the various algorithms available to solve the formulae, that is MDB formulation. One is about the DQN for discrete, and PBOSOC for continuous solution, and finally the curriculum learning and prioritized replay. These are all the different algorithms used to solve the MDB formulations. And the safety and the stability. So the constrained RL shields CBF's safe exploration, right? So these are all the main safety and stability factors about the that RL, for especially for the smart charging. So the next one is about the multi-agent coordinators and vehicle to grid operations. First one is about the distributed control. So instead of centralized scheduler, each charging station actually feed or act as a autonomous agent. So each agent learns a local policy to manage the EV charging as well as the BES within its feeder. So this is the main advantage of the distributed control. And a consensus-based optimization across stations will be used here for the sake of optimization. So instead of depending only one station, all these stations will be taken into account, and it starts to perform the optimization by considering the consensus-based optimization. So instead of considering one station, all the stations will be taken into account. Then the V2G strategies. Actually, normally we use grid to charge the battery when we need to charge it. But in addition, we can return back the energy to the grid also. It's nothing but V2G strategy. So now the power will be sent back to the grid, right? So from consumers to prosumers. So vehicle to grid will be done. It is extended to the EVs from consumers to the prosumers. So that we can maintain the grid stability within the limit. So especially during peak saving, the frequency support, the energy arbitrage, these are all the issues, and battery wear modeling, reward cost, all those things will be taken into account to perform the V2G strategies. And the communication aspects, actually when we prefer the distributed control, we need to create communication among the various stations. So we go for a distributed plus V2G control depends heavily on communication reliability. So why? Because in case of any issues like parameters latency or packet loss or any other cyber security hardening, it will affect the implementation of the multi-agent coordination, especially in the V2G. So all these things must be taken into account to implement the scheme more effectively. So this is what about the multi-agent coordination and V2G. And finally, the evaluation and benchmarks. So these are all the metrics are taken into account. So whatever the metrics we already discussed in the KPIs, everything taken into account here to measure the performance. So the in the economic aspect, actually energy cost, demand charges, and the income revenue will be taken into account. Then in the environmental aspect, the CO2 intensity, renewable energy sources, utilization, sharing, everything will be taken into account. Then the operational point of view, wait time, service level, the curtailment, all those things will be taken into account. And based on the reliability aspect, the constraint, violations and resilience will be taken into account towards the grid. So these are all the KPIs taken to evaluate the performance of the AI system implemented. And the experimental design actually have a comparison like rule-based versus AI, and we can have a forecast and perfect information, and we can do the stress test like extreme weather and high arrivals, and the public data sets can be used to evaluate the model what we developed. So the next one is about the deployment, how just we are going to implement. So developing an AI model in the lab is not often enough. Actually, it must be deployed in real-time, real-world charging networks. So the deployment strategy involves the following: the edge inference for low latency decisions, and cloud for a heavy training and analytics. And the MLOPs must practices the model registry and versioning, and then it's a canary release for safe rollouts, and the KPI key parameter, right, dashboards for the monitoring, and it should be scheduled retraining and rollback plans, and it must allow to operate, that is to perform the interoperability, so that we just prefer whatever the points we listed here, right? So for the service and inference, we go for edge inference for latency. So for in case of local area network to exchange the data, we go for either MQTT or other corresponding protocol. And for the sake of monitoring, we go for the KPI dashboard, where everything will be displayed in terms of user useful information data. And so interoperability that helps you to work with any brand chargers or any brand charging stations we can operate. So these are all the requirement of the deployment and the MLOPs. And finally, the cyber security. So when we go for vehicle to grid operation, actually where energy trading takes place, so we need to perform the during automatic payment, all those things, the security is very important. So to avoid the spoofed telemetry and price manipulation, we must consider the threats. And then in the control aspect, actually, we must consider the mutual TLS like handshaking issue and signed configurations, and RBAC zero trust. And safety point of view, we must provide fail-safe defaults, power limits, and also we must have a human in the loop to check frequently the performance. And again, the same standard of communication protocols must be used here So these complaints make assure the entire system, the functionality in a assured manner. So this case study actually here for the just sake of understanding how the energy cost, peak demand, and the renewable energy user interface improved. So in tomorrow's simulation, it is planned to simulate this setup. So actually in this scenario, 30 charges are taken into account, and it is 1 megawatt feeder is also available to take power from the grid. And a 500 kilowatt hour battery energy storage system is also available, along with a PV power of 300 kilowatt. So here, just for the sake of understanding and comparing the AA performance, both rule-based scheduling as well as the AA approach used here. So when we do compare with existing, the AA-based approach results the saving of energy cost from minimum 12 to maximum 20%. So whatever the cost already spent for charging, from that amount, about 12 to 20% can be energy cost may be saved. And similarly, we can manage the peak demand. So without AA approach, the rule-based system results maximum peak demand. From that maximum peak demand, 25 to 35% can be reduced by applying the AA approach. And finally, the effective integration of the renewable energy sources like PV and wind. So by a good prediction forecasting of renewable energy sources, we can increase its utilization from 15 to 25% when compared with the rule-based scheduling, right? So these are all the outcome. So in the tomorrow simulation and that is validation, where we can check the model and we can run it. We can run different models to find out its performance. Okay, so finally, I would like to conclude my presentation. So that AA enables cost-effective, low-carbon, reliable EV RES integration. So that so when we go for AA, we can definitely we can design the system more cost-effective, and definitely we can reduce the carbon emissions. So why? Because whether the vehicle is made up of EV instead of IC engines, again we depend grid only. So actually, only by integrating renewable energy sources, then only we can reduce this low carbon. So that EV RES integration along in a real charging stations must be properly integrated and properly implemented and optimized to reduce the low carbon. And actually, hybrid stack preferred here to perform the best in practice. Why? Because it needs three different aspects of programming method to implement the optimization. So forecasting, model predictive, and then reinforced learning. So these three involved in AI that increase the overall performance day by day by learning in practice. And the next one is about the AA offer the edge cloud co-design, safety and compliances are essential. So when we try to exchange the data for better utilization and for scalability, the data must be highly secured. Okay, so all those things must be compliant with the standards. So standards are already there. We must follow the compliance so that we can design AI with more effectively. And open opportunities are available in the digital twins. So digital twins is nothing but what again similar to MPC. Actually, digital twins we are just going to implement the real world by digital data. So by running the digital system data, we can we can forecast the response from the real system. So these are all the open opportunities available today with typical integration of the AI. So these are all the reference. Thank you. So any questions?
Participants, any queries, any questions? Do you have any questions? Please type in chat box. Otherwise, directly discuss with our resource person. Any queries?
No, ma'am. Thank you so much. Very effective presentation it was. I really liked the presentation and very point to point, everything was explained. So I'm really thankful to Sir, and with great efforts, he has come out with, this PPT and very precise PPT. I really liked it. Thank you so much, sir.
Thank
Thank
you,
you,
sir.
sir. Thank you, sir. Thank you, sir. Anything? Anybody? Okay. Thank you, sir. Thank you for your valuable presentation. Really
Thank you, madam.
helpful to our participants in AA algorithms. Tomorrow we are expecting more in a simulation of electric vehicles. Okay, sir. Thank you, sir.
Thank
Thank
you.
you, sir. Thank you so
Thank you,
much.
madam. Thank you.
Dear participants, before moving on to the next session, I would like to make some announcement regarding tomorrow's session. Tomorrow being the last day of our 6 days faculty development program, ATAL sponsored faculty development program. And the session will be starting from 2 p.m. onwards. Unlike first 5 days, we used to have 6 to 9, 2 sessions per day, but the last session will be from 2 p.m. onwards. Therefore, all are requested to join by 1:55 sharp so that we can start the session by 2 o'clock. There will be 3 sessions. One session I'm going to handle. I'll be briefing about the sustainable pathway for the future. And the remaining 2 sessions will be handled by Nagarajan sir. He'll be talking about more about testing and simulation aspect of EV. That will be more useful to you, those who are especially now pursuing PhD in the area of electric vehicle. So, and after the session, as per the norms, there will be a online test. So to claim your certificate, everybody must appear for this test. Test will be scheduled between 6:30 to 7:30. Then there will be a formal validity function, which is scheduled from 7:30 to 8 o'clock. And 8 o'clock, we will be posting the attendance, or after the session also. We may not know because we wanted to keep that time surprise, because most of the time I could see more participants towards the end of the session. So it is for the benefit of every individual. Therefore, I expect all your active participation, especially on last day of tomorrow. And hopefully you all will join by 2 o'clock sharp, and it will go up to 8 o'clock. So keep yourself free for tomorrow so that we can have a wonderful and successful conduct of that 6 days FTTP. Ma'am, second session speaker is ready. What is the status?
Within 5 minutes, sir.
Okay.
5 minutes, she will join, sir.
Meantime, we can have a virtual group photo. Can you switch on your video for a moment? We can capture the moment. Thank you. So you can take 5 minutes coffee break. Then we can start the next session.
Sir, I have a request for tomorrow.
Yeah. Tell
Sir,
me.
from 3 to 4, I'll be busy because tomorrow is our working day in our university. And we have a meeting with Vice Chancellor.
Okay. Okay.
So from 3 to 4, I will be a little busy. I'll be attending the session. It will be on, but I might not be
No problem.
able to, in case
Understand.
respond. Just for that span only, I'll request an
Please make
excuse.
sure that you have 80% of the attendance. Now,
Sir,
because
I'm
we
coming
have to
daily,
send
sir.
the proof. We have to send the proof.
Yeah, I'm coming daily, sir. Don't worry.
Yeah. Understand.
Yes, sir. Thank you so
Okay.
much, sir. Thank you.
Continuously he attended, sir.
Yes, sir. Yes, ma'am. Thank you.
Yes, sir.
Sharing, ma'am. நாளைக்கு 3 ல இருந்து 4 வரைக்கும் I'll be a little busy. So, attend பண்ண முடியாது. So, I hope that's okay.
Actually, tomorrow having a wonderful session on both the simulation side and also
Yes. I personally chose this.
Try to attend, sir. No problem.
Yeah, I personally, attended this FDP because I'm a professor of automotive design. So we need to guide a lot of students regarding what is EV and what are the upcoming design trends and technologies. So that's why I have attended this. It's a little bit tough for me from the engineering point of view because I'm not an electrical engineer, but it's very interesting to know a lot of things. So I'm really grateful for this FDP. Thank you so much.
You're welcome.
Thank you, sir.
Thank you, sir.
Ma'am, speaker is ready. We can move on to the next session.
Arunya, ma'am, can you hear me, ma'am?
Yes, I can hear you.
Okay, ma'am. Thank you, ma'am. Welcome you, ma'am, for second session of this day. Okay, ma'am. You can start, ma'am.
Okay, we can start.
Ma'am, anything problem?
Okay. I have to start, huh?
Yes, ma'am. You can start now, ma'am.
Good evening, participants. Today I am going to give some outline about the system design and architecture of EV charging network. The world is witnessing a rapid transition from fossil fuel-based transportation to electricity mobility. This shift is not just about replacing engines with batteries. It is about building a smart, resilient, and sustainable ecosystem that can support millions of electric vehicles in the coming years. But EV charging networks come with their own set of challenges, from grid stability, peak load management, and power quality issues to ensure reliability, accessibility, and cost effectiveness. This is where system design and architecture play a crucial role. A well-structured charging network begins with grid connection components like transformers and switchgear, integrates smart distribution systems, and extends to the end user through charging stations. Adding AI allows us to bring intelligence into the system like predicting demand, balancing load, optimizing charging schedules, and even enabling vehicle to grid interaction. Moreover, coupling the charging network with renewable energy sources such as solar, wind makes the system greener and reduces dependency on fossil fuel-based electricity. With the integration of energy storage solutions and AI-driven energy management, we can achieve a charging infrastructure that is not only efficient but also sustainable. With this introduction, I have started my presentation. So my presentation cover the overview of EV charging network, system design consideration for EV charging networks with AI, role of AI in optimizing EV charging networks, some case studies related to this, and issues and challenges in EV charging, mitigation strategies, system design and architecture of EV charging network with AI and renewable energy, and case study related to that. So this is my plan for today's presentation. The growing demand for EV charging is due to rising EV adoption, government policies, environmental concerns, technological advancement, consumer convenience. So these factors will give rise in the requirement of EV charging in today's trend. So in olden days, we were dependent on fossil fuels, IC engines for transportation like that. We are dependent on fuel. But today we are moving from fossil state to green energy state. So in green energy, we have to use the renewable sources like solar, wind. So from that, we have to generate power. That power is used for vehicles to drive. So the demand for EV charging is raised for a long years. This bar graph shows the EV sales trend in India. So in the bar graph, green color represents current year, that is 2023 status, and orange color represents Jan to June 2024 status. Okay. So by comparing that, for an entire year, the EV registered in the year 2023 is 9 lakh, but for 6 months, the EV registered in the 2024 is above than 5 lakhs. So this is for electric two-wheeler case. For three-wheeler case, when compared to the 2023, the registration units are increased. That is in somewhat in percentage wise, we compare both the years. There is a rise in the sales of EVs. And line diagram, blue color represents EV penetration out of total vehicles in Jan to June 2024. And lavender color represents percentage of EV out of total vehicles in year 2023. So by comparing the lavender and blue color line for a 6 months, the EV penetration is more than the 2023 status. So this is the case. So from this, we infer that EV sale is tremendously increasing from the previous year to the current year. And this is the global electric vehicle stock taken from the source IEA over the world. So here light blue color represents China, dark blue represents Europe, green color represents United States, and dark green represents others. So in EV, China will play a major role. Then this is a bar graph, gives the details about global EV fleet from 2020 to 2030. So according to IEA, the fleet should be reached 230 million by the year 2030. Then public charging points in the year 2022 is about around 55%. So according to this status data, we are moving from diesel transport to renewable energy transport. So we have to give a special attention to the EV charging network, which can be integrated with AI and renewable energy. So now we have to see about the overview of EV charging network. EV charging infrastructure is the system of hardware, software, and grid components required to supply electrical energy to electric vehicles. This EV charging network includes charging stations, power supply networks, energy management systems, and communication platforms. These are the basic blocks for EV charging network. This network enables efficient and reliable charging of electric vehicles by managing power, delivery, user access, data exchange, and so on. So this is the basic block diagram for the EV charging. So in this block, we have grid, that is power from charging, and EV is drawn from the utility power grid, which supplies alternating current. Second block is transformer. This transformer used to step it up or down the voltage. It provides isolation between the high voltage grid and the EV charger for safety also. And third block is rectifier. It converts the incoming AC power to direct current, since EV battery stores energy in DC forms. This can be implemented with diodes or control rectifiers like thyristor, IGBTs, and so on. Next block is DC to DC converter. It will regulate the DC voltage and current coming from the rectifier. It controls charging modes such as constant current and constant voltage. Then last block is EV battery. The conditioned DC power is finally delivered to the battery pack of the electric vehicle. So these are the blocks which is available in the basic EV charging unit. So from the grid, it is stepped down to a required value and it is converted to DC, and the DC is again converted and it is applied to the EV. The key components in the charging networks are EVSE, power electronics, grid connection, renewable integration, networking and communication, user interface and payments. These are the main key components available in the charging networks. EVSE means electric vehicle supply equipments. It covers cables, connectors, meters, safety devices. In renewable integration, we are using photovoltaic battery energy storage system or wind. Network communication mainly used as OCPP, ISO 15118, mobile apps, and user interface and payment is done with the help of apps, RFID, cards, UPI or EMV. So let us see the components in detail. First component is electric vehicle supply equipment or charging station. It is a physical charging point where EV is connected to draw electricity. It converts the grid's AC power to DC power suitable for charging the EV battery. Different types of charging station exist, including level 1, it is a slow charging network, level 2, medium charging network, and level 3, fast DC charging network. EV charging requirements depends on the specification of EV batteries, as power must be supplied to the battery at the right voltage and current levels to permit charging. So in this table, we have vehicle segments, battery capacity, and battery voltage. So E2, that is electric two-wheeler vehicles and electric three-wheeler vehicles, are powered by low voltage batteries. The first generation of e-cars is also powered by low voltage batteries. However, these are all likely to be phased out in future, even if they continue in the specific use cases such as taxis. The second generation e-cars, as seen in the upcoming e-car models, is powered by high voltage batteries, electric light vehicles will comprise of both low voltage and high voltage vehicles depending on their load carrying capacity. So this slide shows the charging methods. EV charging involves supply of direct current to the battery pack. As the electricity distribution system supply alternating current power, a converter is required to provide DC power to the battery. Conducting charge, that is wired charging, can be AC or DC type. So here the left represent AC charging, right represent DC charging. So here the main components available in this charging method, we have 4 modes of operation: onboard charger, AC to battery, then some connectors. So mode 1 and mode 2 are applicable for connecting an EV to a standard socket outlet utilizing a cable and plug. Mode 1, also known as a dumb charging, permits no communication between the EV and EVSE, and its use is not recommended. The portable cable used in mode 2 has an inbuilt protection and control capability and is typically used for home charging. Mode 3 and mode 4, which provides a separate charger device to supply power to the EV, have improved control system and are used for commercial or public charging. This charging is classified into so many types based on power levels. A type of charging is classified as level 1, level 2, DC fast charging, ultra fast charging, and so on. Based on location, the type of charging is classified as home charging. Home charging means private garages, apartments, like workplace charging, public chargings like malls, highways, parking, fleet and depot charging like buses, trucks, taxis. Then EVS power rating, this is one of the main factor for deciding the EVSE. EVSE have different power ratings or levels based on charging requirements, which in turn determine the input power requirements for charging infrastructure. So for two-wheeler vehicles, three-wheeler vehicles, e-cars, we can prefer normal power charging. For e-cars, light vehicles and medium light vehicles, that is around 1 to 6 tons weight, these vehicles are needing high power charging. So for normal power charging, the current type may be a AC or DC. For high power charging, the current type only a DC, and the power levels are given here. So based upon the power level, we are preferring normal charging or high power charging. Then next component is central system management software. It is a brain of charging network. It will monitor and controlling charging operations. It handles user authentication, payment processing, load balancing, and data logging. Then second component, communication infrastructure. It includes the network protocols like Open Charge Point Protocol and hardware that allows the charging station to communicate with the CSMS and other network components. It ensures interoperability between EV chargers from different manufacturers and the charging network operator software. It ensures seamless data exchange and efficient operation. Then OCPP architecture and data flow. So here we have a charger. This charger is acted as a backend communication. When a EV plugs in, the charging station communicates with the backend via OCPP. Then the message is authorized via RFID or some application. Then backend validates the user. Charging starts. Energy consumption data sent back. Then the charging process over. The backend handles the billing. Okay, the flow of this architecture is when we connect the EV vehicle to the plug, charger will authorize and validate and start charging, and energy consumption data sent back, then charging process over, then the backend will handle, that is, it will deliver the building status. Then deployment models in OCPP. So deployment model is a technical or structural setup. That is how the charging network architecture is organized. There are 4 models. One is direct to cloud model. So in this, charger directly talks to central backend. Local controller model, charger talks to local gateway. Hybrid model, both communication takes place. Standalone model, offline charges, there is no backend in here. Then deployment approaches, it is a business or policy strategy. That is who invests, owns and operates the infrastructure. There are 4 approaches: public-private partnership, utility-led deployment, private charging operators, government-backed programs. Then the next thing is renewable integration. So this diagram shows how the renewable is integrated to the DC bus, and from the DC bus how the DC supply is taken to the electric vehicle, that is plug-in electric vehicle. So we have a solar, utility grid, energy storage. From this we have used some maximum point tracking concept in solar, and rectifier in utility grid, and bidirectional converter in energy storage in their power transmission side. So after this we have a DC, that is DC is fed to the common DC bus. From the common DC bus the supply is taken or it is given to the plug-in electric vehicle. Here energy storage, we have a 2-way communication, that is from energy storage unit to the power flow is from energy storage unit to PEV, or from PVE to energy storage unit. So that here we have a bidirectional. The next component, supporting system. Energy management system is one of the supporting system. It is used for load balancing and peak saving. Then other supporting systems are smart charging and AI optimization schedule. It is a function of this is charging to reduce cost, optimize renewables, vehicle to grid EVs. It will provide power back to grid. That is sometimes if you are using a microgrid concept, suppose microgrid failed to give a supply to the EV vehicle, then we can directly take the supply from the main grid. Then billing and payment gateway integration, these are the supporting systems in the EV charging network. Other components like utility, smart grids and energy storage. So modern architecture may also incorporate smart grids and energy storage solutions like batteries or fuels to optimize charging and minimizing impact on the grid. Then architecture layer. So this architecture layer of EV charging contains 5 layers: physical layer, communication layer, controller layer, artificial intelligence layer, user layer. The physical layer, it consists of the hardware components such as chargers, transformers, and energy storage systems form the foundation for energy flow and supply stability. The communication layer ensures connectivity using IoT devices, 5G networks, and standardized protocols to exchange real-time data between chargers, grid infrastructures, and control system. The control layer manages operations through smart meters, SCADA systems, and demand response programs, enabling efficient monitoring and balancing of loads. The AI layer adds intelligence by using forecasting, optimization, and fault detection to predict energy needs, improve efficiency, and detect anomalies early. The user layer provides customer interaction through mobile applications, billing systems, reservation platforms, making the system user-friendly, and accessible. Together, these layers create a robust, intelligent, and consumer-oriented energy ecosystems. The architecture of the EV charging can be classified into three types. One is common AC bus architecture. Here, multiple charging stations are connected to a common AC bus, which then connects to the grid. Okay, the structure of the AC bus architecture is like this. We have a grid supply. From the grid supply, we have the transformer. So this transformer either step up or step down the value, and it is connected to the common AC bus. So from the common AC bus, multiple EV vehicles are charged through power electronic converters. Then common DC bus structure, it is more efficient and cost effective for high power charging. The same thing, but here we are using a rectifier circuit. The output of the transformer is given to the rectifier circuit, and the rectifier output is given to the common DC bus. From the common DC bus, electric vehicles get powered. Then microgrid architecture. A microgrid enabled EV charging architecture ensures self-sufficiency, reliance, and greener energy use, with AI making real-time decisions on when to draw from solar, battery, or the grid. So here we have a renewable energies like solar, wind. So from that we extract the power. That power is stored in the storage system. The output of the storage system is connected to the microgrid controller. The output of the microgrid controller is given to the EV charging station. If microgrid get failed, then the grid is directly supply the voltage to the EVs. Next, we see about system design consideration for EV charging networks with AI. First one is electrical and grid load assessment. That is a peak or average value, diversity factor, feeder capacity, transformer upsizing, then AC versus DC mix, connector types, CCS2, and so on. Power quality, on-site generation, storing, sizing, islanding or microgrid logic, V2G or V2H enablement. These are comes under electrical and grid. That is, careful load assessment is needed to size feeders and transformers, considering peak demand, diversity factors, and harmonics, choices between AC and DC charging, connector standards, and integration of on-site solar batteries and microgrid logic ensures grid stability. Future readiness includes V2G or V2H capacities following IEEE and ISO standards. Second one is site and hardware. It involves physical design of station layout, cable routing, accessibility, and weather or thermal protection, redundancy, and revenue grade smart meters improve reliability and accountability. Communications and interoperability. Here we are using open standards like OCPP 1.6 bar 2.0.1, ISO 15118, and OpenADR ensure charges talks to vehicles, utilities, and backends. Connectivity through Ethernet, 4G or 5G, Wi-Fi with offline failover maintains uptime. Then control and cloud architecture. Local edge controllers provide real-time fallback, while cloud platforms handle orchestration, role-based access, and observability. Data pipelines combine streaming analytics with time series and cold storage for long-term optimization. Then AI and analytics. Here AI enables demand forecasting, dwell time prediction, optimal charge scheduling, and dynamic pricing to balance grid loads. It also supports predictive maintenance by detecting anomalies in EVSE telemetry and renewable energy forecasting for battery co-optimization. Then cyber security and privacy. It secure boot, TLS encryption, PKI-based plug and charge, and segmented networks protect against attacks. Compliance with CRT, IN, or local cyber security guidelines ensures incident reporting, log retention, and user privacy. Reliability and resiliences. Here systems are designed for high uptime, graceful degradation during stress, black start procedures, remote monitoring, and quick fault recovery through spare strategies. Then user experience and operations. For drivers, features like reservation system, multiple payment option, real-time availability dashboards improve adoption. Then compliance and safety. EVSEs must follow electrical codes, interconnection standards, fire safety, ventilation, and emergency protocols while meeting permitting and accessibility norms. Business and economics. Operators must evaluate total cost of ownership, tariff strategies, and utilization targets to ensure financial viability, supported by government incentives like FAME or NEVI. Then key performance indicators to track. Here, key performance indicators include uptime, connector utilization, kilowatt hour per session, revenue per day, wait times, grid peak reduction, and predictive maintenance accuracy. Next, we see about role of artificial intelligence in optimizing EV charging networks. So this role of AI is in many fields: demand forecasting and load management, dynamic pricing, charging station placement, renewable energy integration, fault detection and predictive maintenance, and so on. So this slide shows the role of AI in many fields, that is optimizing charging location, demand forecasting and scheduling, grid stability, load balancing, battery management, cost reduction, enhance user experience, renewable energy integration, fault detection and predictive maintenance, interoperability, and smart grid support. So how in optimizing charging location AI is used? AI analyzes data from existing charging station, including usage pattern and geographical information, to identify optimal location for new stations. This ensures that charging stations are placed in areas with high demand, improving convenience for EV owners and maximizing the utilization of infrastructure. In demand forecasting and scheduling, AI algorithms predict future charging demand based on various factors like time of day, day of the week, weather condition, and user behavior. This enables the development of optimized charging schedules, allowing for efficient energy distribution and reduced strain on grid. AI can also leverage time of use rates to encourage charging during off-peak hours, further optimizing energy distribution and reducing cost. Then in grid stability and load balancing, AI-driven demand response system can dynamically adjust charging schedules based on real-time grid conditions, energy availability, and predictive analysis. This helps mitigate the duck curve effect, which refers to the fluctuation in electricity demand, and ensures grid stability by coordinating charging with periods of high energy output. AI can also manage capacity by dynamically changing pricing based on demand, optimizing energy distribution, preventing grid overload. Then battery management. Here, AI-powered battery management system can accurately estimate battery state of charge and state of health, enabling reliable range prediction and efficient energy use. AI can also optimize charging speeds and patterns to maximize battery lifespan and performance. Then in cost reduction, by optimizing charging schedules and leveraging dynamic pricing, AI can significantly reduce charging cost of EV owners. AI-powered system can also identify and address potential issues with charging stations, minimizing downtime and reducing maintenance costs. End-user experience, AI-driven solution can provide real-time information about charger availability, estimated charging times, optimized charging routes, enhancing the overall user experience. AI-powered route optimization can also minimize downtime for EV fleets, especially in last-mile delivery and ride-hailing service. Then in renewable energy integration, AI forecasts solar and wind generation and aligns charging schedules. It reduces reliance on fossil fuel backup. In fault detection and predictive maintenance, uses SCADA plus IoT sensors to detect anomalies in charges. It predicts failures and reduces downtime. Interoperability and smart grid support. Here, AI ensures communication between different charger types, operators, and the grid. It supports vehicle-to-grid energy flow optimization. Some of the case studies related to artificial intelligence in EV charging networks. First one in India, Tata Power Electric Vehicle Network with artificial intelligence load balancing. Tata Power has deployed one of the largest EV charging networks in India, integrating AI-based load balancing to optimize feeder and transformer utilization. By forecasting peak demand and redistributing loads, the system reduces stress on the grid while ensuring faster turnaround for EV users. AI models also help integrate renewable sources like rooftop solar for sustainable charging. Second case study in Europe, AI-assisted smart charging with vehicle-to-grid project have implemented with AI-driven scheduling. Here, EVs not only charge but also feed energy back into the grid during peak demand. AI algorithms optimize the charging and discharging cycles based on dynamic traffics, tariffs, renewable generation, forecast, and user-driven patterns, making the grid more resilient and flexible. Then in USA, Tesla superchargers with AI predictive maintenance. Here, AI-based predictive maintenance and analytics to minimize downtime. Sensors embedded in EVSEs send real-time telemetry data, which AI models analysis to detect anomalies, predict failures, and recommended proactive services. This reduces mean time to repair, ensures high uptime, and enhances the charging experience for drivers. Then we discuss about the issues and challenges in EV charging. First one is power quality issues. Harmonics. EV chargers use power electronic converters, that is power electronic devices, which will introduce harmonic distortion into the grid. So the THD, total harmonic distortion, get increased. It will affect the sensitive equipments. Then voltage fluctuation. Here, fast charging stations draw sudden large power, which leads to voltage dips or sags in weak grids. Unbalanced load. If EV charging is uneven across phases, it causes voltage or current imbalance in three-phase system. Flicker. Rapid changes in charging loads. Example, multiple EVs connecting or disconnecting. Visible light flicker and disturbance. Reactive power demand. EV chargers may consume reactive power if not corrected. It reducing power factor and increasing losses. Then transformer overloading. High penetration of fast chargers creates thermal stress and reduced lifespan of distribution transformers. Harmonic response. Interaction of charger harmonics with grid impedance may lead to resonant condition. This will amplify the disturbance. Frequency stability. In weak or islanded microgrids, large EV charging demand can disturb system frequency balance. Grid integration challenges. Here, high demand during peak hours create a stress on grid. Unbalanced load in three-phase system also affect the grid. Frequency stability issues in weak or microgrids. Charging infrastructure limitations. This is one kind of issue, that is insufficient public charging stations, uneven distribution in the urban and rural areas, long charging times compared to refueling internal combustion electric vehicles. Then economic and cost issues, high installation maintenance cost of fast charger, land acquisition and utility connection expenses, cost of electricity tariffs for consumers, cyber security and communication, EVSE connected to cloud and apps, so risk of cyber attack is more, data privacy concerns, interoperability between different networks and standards, renewable energy integration. Under this, the challenges or issues are variability of solar or wind may affect reliable charging, with need for storage to balance fluctuation, lack of smart grid integration in many regions, policy and regulatory issues, lack of uniform standards for connectors and payment systems, slow government approvals and unclear business models, utility companies resistant to invest without clear ROI. Then user-related issues, range anxiety and fear of charger unavailability, long queues at limited fast charging stations, lack of awareness about optimal charging practices. How these issues are rectified? So first one is smart charging. By using smart charging and AI load management, vehicle to grid and demand response programs, government subsidies and public-private partnership, standardization of chargers and payment system, renewable storage, hybrid charging stations, use of active front-end rectifiers with power factor correction, installation of harmonic filters, smart charging and AI-based load management to balance load, strengthening distribution transformers and feeders, then smart grid and interoperability, integration with smart grids, AI ensures grid stability during high charging demand, use of national energy data standards, SCADA formats. So these are the tips for reducing the issues or facing the challenges. Then in future, ultra fast charging is possible, wireless or inductive charging is happen, AI driven predictive charging is happen, renewable power charging hubs are available, vehicle to everything concept is there, vehicle to grid with AI is there, AI plus blockchain for secure transaction, autonomous EV fleets with self-charging networks, these are comes in future. Then we see about the system design and architecture of EV charging network with AI and renewable energy. So first step is extended layer architecture. In this we have vehicle and connector layer, power conversion layer, renewable energy layer, AI or smart energy management layer. So in vehicle or and connector layer, we have AC to DC connectors, safety, ISO 15118 guidelines, V2G concept. In power conversion layer, we have AC to DC chargers with modular rectifiers, bidirectional inverters for V2G or V2B or V2H, hybrid inverters for photovoltaic plus battery energy system plus grid coupling. In renewable energy layer, we have on-site solar PV coupled via hybrid inverter, wind or microgrid tie-in, energy storage, batteries, supercapacitors. And in AI smart energy management layer, it will do the load forecasting based on EV arrival, state of charging, dwelling time, renewable forecasting, dynamic load management, optimal scheduling. These are present in the external layer of AI smart energy management. Then next layer is control and software layer. Here we have AI algorithms, cloud-based CSMS. In AI algorithm, reinforcement learning for charging optimization, predictive analytics for component failures, blockchain enabled energy trading. These are comes under control and software layer. Then in grid and market layer, we have grid services via V2G. So it will do the frequency regulation, voltage support, and TOU tariff optimization, participation in local energy marketing. These are comes under grid and market layer. Then renewable integration architecture. So here we have 4 steps. One is daytime. That is how the renewable integration architecture works. Okay, during the daytime, for PV supplies, electric vehicle, and also battery. And if any surplus energy is there, then it is fed back to the battery. During the night time, battery and grid supply the EV load. During the cloudy or high load time, AI decides mix, that is by using grid and partial storage from battery is used for charging the electric vehicle. Fleet deposits, AI ensures full charge before dispatch using forecast and renewable scheduling. So these are the 4 way of concept followed for charging the electric vehicle while integrating with renewable energy. Then benefits of this one is sustainability, economics, resilience, user satisfaction. So when integrating the AI, we get a continuous supply with low carbon footprint. Then economic wise also, we have a benefit. Then if any disturbance occurs, then AI and will rectify it and it comes to the normal state. The system comes to the normal state. Then user also gets satisfied because of lower cost and reliable charging. So one of the real-time example is solar power AI-driven EV bus depot. So it is installed in Bangalore, India. The fleet size of this project is 50 electric buses with 60 to 120 kilowatt hour per bus. Here the charging type used is DC fast charging, that is 60 to 150 kilowatt per bay. Then the dwelling time is overnight 8 to 10 hours plus midday top-ups. Objective is minimize grid demand, maximize renewable utilization, optimize bus availability. So in this Bangalore project, the system architecture is like this, that is power sources used is 1.5 MVA feeder, on-site solar PV is 500 kilowatt, DC coupled with a battery energy storage system. Energy storage system capacity is 200 kilowatt hour and lithium ion battery is used. Charging infrastructure consists of 50 DC chargers, modular 60 kilowatt each, liquid to cooled cables for continuous operation, AC chargers for depot staff, load management via AI-driven EMS. Then in control and AI, predictive load scheduling for buses based on route and SOC, AI forecast for solar generation and grid demand, dynamic charging rate allocation to minimize energy cost and peak demand charges, vehicle to grid enabled for emergency peak saving. Then in communication and software side, They are using OCPP 2.0.1 for backend integration, ISO 15118 plug and charge with secure PKI, cloud-based dashboard for operators, real-time analytics, and preventive maintenance. Design consideration for this project is given in this slide. Peak site load 1.8 megawatt, transformer size 2.5 MVA, solar integration, PV supplies 30 to 40% of depot consumption, battery energy storage system usage, charge during solar peak or off peak, discharge to reduce grid demand. Then AI optimization used for minimize energy cost, avoid peak grid load, schedule bus readiness, and the safety side, they are using type B RCD for DC chargers, SPDs T1 plus T2, liquid cooled connectors, fire and thermal sensors. Then monitoring, remote diagnostics, KPI tracking, uptiming greater than or equal to 98%, MTTR less than 2 hours. Then operation workflow of this project is evening arrival. During the evening arrival, AI schedules buses to DC charges based on SOC and departure time. Dynamic charging, EMS adjust charger current based on PV availability and battery SOC. Midday top-up, optional short charging for buses with high route requirements. Data feedback, real-time data sent to cloud for predictive maintenance. AI model training, V2G optional during grid peak hours, depot battery energy storage system plus selected buses discharge to reduce peak load. This is the operational workflow. Then the results or benefits from the project are energy cost saving, that is 25 to 30% reduction via solar and AI optimization. Then grid peak reduction is approximately 15% lower demand charges. Then availability, 100% buses ready for scheduled routes. Maintenance, predictive alerts reduced unexpected downtime by 20%. Then carbon impact, 200 terawatts CO2 emission per year avoided. That is due to renewable energy. So I come to the end of the presentation. So in this presentation, we have seen the overview of EV charging, system design consideration, implementation of AI in charging network, some of the case studies and benefits. These are discussed in this presentation. So I have concluded my session with EV charging networks need robust design and AI backbone. AI ensures efficiency, reliability, and user-centric smart charging. Thank you. Any queries, please ask me.
Participants, do you have any questions? So today's attendance and feedback link has been posted in the chat box. You are requested to give your attendance and submit your feedback. Thank you so much, ma'am, for your wonderful presentation. And one more reminder to all the participants over here. As I said earlier, tomorrow's session will start by 2 p.m. onwards. There will be 3 sessions tomorrow, 2 to 3:30, 3:30 to 6, and 6 to 7:30. And as per the norms of ATAL Academy, we have to conduct online test to claim your certificate. So there will be 1 hour online test. So we'll be posting the Google form in the chat box. and 1 hour will be given. You have to give your answers accordingly. Evaluation will be done. So that mark will be given to ATAL Academy for further processing of certificate. Therefore, I request all the participants to attend tomorrow's sessions without fail. Otherwise, there is no use of attending the past 5 days. The assessment will be purely based on tomorrow's session. Therefore, don't miss out tomorrow's sessions. And there will be a validatory session between 7:30 to 8. During that session, you can give your oral feedback about your learning the past 6 days on the chosen topic. So with that, I once again thank all the participants for your wonderful participation until today. I hope the similar kind of response in the tomorrow sessions as well. So until then, take care. Bye-bye. Tomorrow we'll meet by 2 p.m. sharp.
Thank you, sir.
Thank you, ma'am.
அம்மா 8 மணிக்கெல்லாம் முடிச்சிட்டேன்.
Thank you, ma'am. And also thank you, sir.